Good afternoon, everyone, and welcome to the International Biochar Initiative webinar, Biochar Use on Golf Courses. My name is Caroline Peet. I will be facilitating this webinar. Before we get started, just a bit of housekeeping. You should already be able to hear me and see the share screen. If you're hearing echoes or your sound quality is bad, use the audio functions in the GoToWebinar toolbar, which is probably on the right side of your screen. If you still have any trouble, send the organizers a message using the chat feature, and don't worry, we are also recording this webinar. The recording and slides will be available soon after the live event. If you have a question, you may ask it at any time using the questions pod on the GoToWebinar panel. We will handle all questions at the end of the presentation in a discussion with our moderator and our speaker. So thank you for joining us. I'm going to hand it off to our moderator, Kathleen Draper, to lead you through the great presentation we have for you today. Kathleen, you want to take it away?
Yeah, thanks, Caroline, and hello, everybody. Thanks for joining us today. We do have a few folks that might be new to biochar or may not know much about the International Biochar Initiative, so I just want to take a few minutes to let you know who we are and what we are all about. So we are a mission-driven nonprofit focused on fostering a robust, sustainable biochar industry. And one of our primary goals is to connect stakeholders, including researchers, biochar entrepreneurs, policymakers, and potential customers. We do endeavor to promote good industry practices and environmental and ethical standards to support biochar systems that are both safe and economically viable. One of the ways we're trying to accomplish that is by sharing information about successful and promising biochar end uses, business models, and market opportunities. And we do that through these webinars, by publishing topic-specific white papers, and through biochar study tours. More about that at the end of this webinar. Most of our current revenues come from membership fees, and our business and organizational memberships provide needed funding, for which we're very grateful. So I just wanted to give a quick thanks to some of our newest, renewed, or new business members. As it happens, they are all biochar production technology companies, so if you're in the market, you may want to check them out. And those are Rainbow Bee Eater out of Australia, Concord Blue Energy, a German and American company, and All Power Labs out of California. Next slide. Today's webinar is on the use of biochar on golf courses and other managed turf. While we've seen an overwhelming increase in peer-reviewed literature related to biochar, today's webinar focuses on research being conducted in real-world scenarios and framed within pragmatic economic realities. Our presenter today is an award-winning golf course superintendent from Illinois. Dan Dinelli has been involved in testing biochar use on golf courses for many years and has been educating and inspiring others in his industry to do the same. Today, he'll be talking about his learning curve to understanding the complexities of biochar and what worked best for him. Dan, I know you have a lot to cover, so it's all yours.
Thank you, Kathleen. And thank you, everyone, for joining in and having me as your guest. This is, I'm going to confess, my first podcast. I'm kind of used to pacing and having a pointer and interacting more with people. So I hope you have questions or comments or things to contribute as we go through this, but I'm going to share with you kind of my journey on what how I learned and what I learned about biochar and its use in turf, specifically on sand-based ridge zones that most putting greens are constructed out of today, what we call a USGA recommended ridge zone or a California ridge zone, which is generally around 90% sand, so it's mostly sand. Next slide, please. So turf grass, though, I think to take just a half step back a little bit, turf grass really offers a lot of wonderful services. It's used a lot, obviously, as a perennial ground cover to have physical activity on and playing sports like golf and soccer and whatnot, and recreation. Good physical activities usually conducted on turf at a safe level. And then environmentally, it's known to be a good plant system that helps purify the air, purifies the water, prevents erosion control, mediates temperature, and generates oxygen. So whenever I look at my practices on the golf course, I try to understand these services and how I can impact them more favorably. And I think you can see how biochar could fit in some of these areas quite nicely. Next. As the population continues to expand and grow, these cities are getting to be the safe havens for humans in the sense that they claim over 80% of the nation will live in urban areas. That's according to a 2010 statistic. So cities are becoming obviously, areas of concern for people for environmental reasons, and these open green spaces are becoming very important. Next slide. Within these areas, when people are asked, for example, in these urban areas, what do you think of when you think of open green space? These are some of the things that data brings out, and things like beautiful, relaxing, peaceful, nature, there's the word exercise in there. So obviously humans recognize this value of open green space, especially among the city setting. Next. And the golfscape is no exception. Golf sometimes gets a bad rap, I think, for, I don't know exactly the reasons, but it is open green space that offers those benefits that turf does offer the system, and often golf courses are more than just turf. Usually they're parking and setting type courses that have a fair amount of trees and shrubs and other plant life that contributes, as well as bodies of water. And again, this contributes nicely to the overall system. Next slide. In fact, turf grass was ranked third behind corn and soybeans with an estimated 60 million acres planted in the United States. So obviously, turf grass is seen pretty common out in the field, but again, many of its benefits, I think, are overlooked, unfortunately. Next slide. So when we look at these benefits that turf and the turf systems, next slide. There we go. Has to offer, again, I try to understand these benefits and how can they be influenced. So now when you start thinking about something like biochar or compost and other things that could help enhance the air and water, soil, the microbiology, its use as a habitat, and the overall ecology, you can see how biochar could be a pretty powerful input in that whole area to the left. It also is an area that impacts jobs, whether you're taking it to biochar or studying it. And then, of course, the human and physical, social benefits that biochar might have to offer. I really tried to understand those things as well as the agronomic influences biochar might have. Next slide. So when I started to study biochar, it was very foreign to me. I didn't really know what it was. I kind of understood charcoal, so I guess in that regard I had some little bit of understanding, but the complexity of how it's made kind of was very fascinating to me. And but I learned that there's a lot of variables in this process, or there can be rather, on how biochar is being generated. Next slide. What probably interested me the most was over a period of time after I started understanding biochar better was the basically the cell structure, the pore space that was left behind, and of course the CEC and the water holding capacity, and ultimately the biology that might come with utilizing biochar, especially in a sandy medium. Next slide. So biochar, with those characteristics, as well as its longevity in the soil, adding water holding capacity and the CEC for nutrient retention and use, seemed like a perfect fit and marriage for these sandy mediums, especially. Next slide. So when I started to understand better about how biochar is generated and all the variables that may exist during this whole process, it kind of reminded me of the learning curve I took trying to understand compost. there's temperatures as part of the equation, feedstocks part of the equation. So it was in soil gases, whether it's CO2 or oxygen, part of the equation. So it's kind of fascinating. I made some parallels in my mind mentally on these different elements that feed into making char. And for example, next slide. You talk a lot about feedstocks and how the feedstock may differ not only in its own nature as far as its chemical makeups, but its cell structure, perhaps the amount of ash that might be generated with these different types of feedstocks, and what that might mean as its use, especially in agriculture. I think I'm going to talk about this a little later, but for example, the research that's been done on turf, the oldest research, they use switchgrass as a feedstock, as a parent material. And they did so in such a way also that they didn't really pre-treat the switchgrass. So I think I'll talk about that a little bit more, but I think most people who study and understand biochar, switchgrass char probably is going to be significantly different than char that's generated from hardwood. I'm not saying it's bad or good or right or wrong, it's just that they're different. And so I think the ultimate goal is whatever you're trying to strive for as an outcome, you just need to understand these personalities that these different materials may have to offer and what to expect from them. Next slide. The other thing I learned was the importance of feedstock prep and the consistency of that feedstock and size and dryness, whether there be contaminants associated with it. So again, it's another variable within the process. Next slide. And then the whole process of pyrolysis itself. I'm still trying to really better understand that whole process, but generally, the temperature that the pyrolysis is being delivered at, for how long is the feedstock under that heat, to what extent is any oxygen present, how it's cooled, and even how it's stored. I've read some papers, for example, that you can take quality char and store it in a, for lack of better words, a polluted environment, for example. Let's say in the back of my shop, I have open bags of char, an open pile, but yet it's right next to where the mechanic brings equipment back and forth, spitting out diesel fumes. That char is pretty hungry stuff, and it's going to start absorbing those types of things and possibly change the characteristic of that char. So, even storing this material can have an impact ultimately on the quality of the material. Next slide. But it seems again that the chemical residue seems to be a component, obviously, on how the char will behave and how it might impact soil and plant health. But much of it does boil down, it seems, in my mind, as the pore space, the type, the size of the pore space of the char, and that's pretty intriguing to me. Next slide. But at the end of the day, to get consistent quality biochar, I recognized is a process, and it can be a challenging process. And as an end user, the one thing you strive for with most of these inputs that are organic in nature, we'll just say, is the level of consistency, predictability of it. So then you can rely on it when you use it, and you know what the outcome is going to be based on the rate and the way it's utilized. It all starts with how consistent is the char as you try to use it as an amendment. Next slide. However, as usual, nature makes it look easy. I found it fascinating reading about how biochar is part of a natural deposit. And we have several acres of prairies, for example, on our golf course and grasslands that we burn. And when we do that burn, the fire gets so hot that you can't really be near it. And you watch it burn, and the tops are burning violently. And as you study down below near the surface of the soil, you'll see the smoke, the smothering, and you don't really see that much flame. It seems like it's flaming off just above the surface. And you can just visualize how the oxygen demand is so high as it burns off that biomass up in the, up further away from the ground, that it's starving the lower region from oxygen, but yet that heat is so high, there's pyrolysis in action right there. And the amount of ash that's left behind, of course, is one thing, but also that black char is another. Next slide. So there's references out there, and I've seen several different numbers thrown around, but at the end of the day, people who study these natural grasslands and prairies and whatnot, they all agree that there's an element of char in the soils from back in the days when lightnings would create these fires naturally, and then later on the Native Americans apparently would burn fairly often to manage that biomass, even the pests of bugs and stuff that burning would offer. So burning was a natural part of the process that really, the next slide, demonstrates how the Corn Belt was developed. If you take that Corn Belt, the map of the Corn Belt, which we recognize goes to the heart of the country, is a very high producing soil and system environment for corn and soybeans. I think we could all be pretty proud, those of us that, believe in the biochar, so to speak, that biochar is a component of that. If you look at that shaded area, and the next slide, overlay that with what the highly productive soils overlay is, the tall grass prairies is the big part of it, the mixed prairie, then the short grass prairies. But the tall grass prairie really generated a lot of that high level tall biomass that really created that strong system of pyrolysis. As the grass gets shorter and the biomass gets less at the surface, I think that mass burns differently and probably more thoroughly, probably leaving less char behind. So you overlay that map, the tall grass prairie and a little bit of that mixed prairie, and that's our Corn Belt. Next slide. So, like I said, there's studies out there that are all interesting, and this one here spoke to specifically Illinois, the state I'm in, and how fires played a role in this multi-level feedback system that sequestered and deposited soil organic matter, enhancing soil fertility. So it's not just theory; science is, demonstrated and proven this. Next slide. This was another study that I read that I found interesting. What they did here is there's a general feeling that when you look at natural ecosystems, that the natives tend to be more competitive when the soil is more impoverished. So if you fertilize like a native prairie, that would be probably considered a poor practice in most cases, because that prairie system doesn't need that extra nutrients, and in fact it may feed Eurasians or non-natives and give them the competitive edge. So this study took a grassland soil in itself as a control, which is that far left bar, and then the BB and the NB are basically two types of biochar that was made from, one was made from a native grass, a little blue stem, and the other one was made from a non-native. And you can see the nutrient content that was in the soil. So you got the nitrate and you got the ammonium. And you can see how adding the biochar from those two different feedstocks really raised the bar on the nutrient levels in the soil. Then they compared that to taking that same feedstock, that same parent material, the native and the non-native grass, and they just took that organic material, non-pyrolyzed, I can't say it, it didn't go through the pyrolysis process, and they just laid that in as an organic amendment. And you can see how it impacted the ammonia component of it, and the overall nutrition. So clearly char is a hungry material that's grabbing onto things. In this case, ammonia is one. And, this also tells me how biochar could be really a good companion in the composting process. That as you compost, generally much of that ammonia gases off and is lost in the atmosphere. Adding an element of char in with that compost during the composting process, you can probably harvest a lot more of that material, meaning the ammonia and ultimately the nitrogen, to be utilized for plants instead of lost into the atmosphere. So I found that study to be very interesting. The next slide, talked about soil organic matter. And, soil organic matter is very complex for me to get my head wrapped around because it's just such a general term. And we speak about soil organic matter at a very, very high level most of the time. In fact, soil test doesn't typically even separate living from dead, let alone to what level of complexity is the organic matter in, and so on. So this study actually studied how biochar affected the cycling of soil organic matter, where soil organic matter was increased, but it was increased probably from the microbial activity as it broke down the plant-derived organic matter. So that's important in a turfgrass system because turf wants to lay down blankets of organic matter, what we typically call thatch or mat. That perennial crop creates that surface organic matter pretty readily. To an ecologist, grasses in general are considered like early in the succession of plants. So they're kind of a pioneer plant. So if you have like a fire or a landslide or anything that disturbs the soil surface and wipes out the existing plant life, typically you'll get lichens and moss and grasses that come in for a period of time, and the fibrous root system grabs a hold of that loose material and it starts depositing organic matter, and basically they're soil builders, and they build the soil for the next succession, whether it be forbs, shrubs, trees, and ultimately climax forest. So knowing that that turf is a soil builder, if you're trying to go sustainable, you need some thatch and some mat in the system for resiliency. But if it gets excessive, the ideal thing is to have a system in place where material is turned over and utilized as a nutrient source instead of a complex high lignin type carbon blanket. Next slide. So when I first looked into biochar and it's used on turf, this study was 2010. There was another one that was from the similar era from Cornell. So I was able to find two studies, one in Iowa, one at Cornell, that studied biochar specifically in sand-based ridge zone mixes, which was my biggest interest. And after reading both those papers, and understanding more about the nature of biochar, I learned a lot from them, but it's also a little unfortunate that even though they spoke positive about the char, I think maybe if they would have done things differently or compared it to other types of char, perhaps the outcome could have even been stronger. What I mean by that is both those studies use switchgrass as a parent material. They use a grass, and it was not pre-treated. So one of the things I learned, for example, is if you take a study and you take raw char and you, especially in a sandy mix, and you establish the turf, and if your fertility, for example, is more standard in nature on its rate and application frequency, if you were to graph the growth of that turf, it would probably show a dip at first. And then as that char gets satisfied with the nutrient load and it starts giving back, then you'll start to see the rise in the value of that char. And so if it's a study like this that's using raw char and a char of grass especially that probably has a lot of ash, probably a fairly high pH associated with it, and it's a short-term study, the outcome may not be as strongly positioned as one that would be a long-term study, or ideally a biochar that has been preconditioned with some nutrients, or perhaps nutrients a little more heavily applied, especially in an impoverished system like sand. You'd probably see much higher level results. So The next slide. So what got my interest in biochar to begin with was understanding how these sand-based systems evolve. And as I mentioned, grass being a pioneer plant, it really has no problems growing in a sandy medium. It's pretty much really at home in it, generally speaking. It's kind of designed and engineered to grow in impoverished systems, as I mentioned, because it's a pioneer plant in general. You know, these are generalities here, but so it's not really on can we improve turf grass growth, even though I think that can still be accomplished, but it's more like how can we improve upon the systems that the turf is growing in and have the long-term outcome be sustainable. And that feeds back a little bit more on that thatch mat layer and root growth, how the plant grows with these different amendments and inputs. The next slide. Going back to over 20 years now, I think this green's 21 years old now. We built a research green. This is probably one of the longest lasting research greens out there. We got a grant to build half of this green that housed what we call the NTEP, National Turfgrass Evaluation Program. And the National Turfgrass Evaluation Program, along with the Golf Course Superintendents Association, the GCSAA, and the USGA, United States Golf Association, about 20 years ago, they pooled funds together and they funded 15 of these greens throughout the country, 5 in the north, 5 in what we call the transition zone, and then 5 in the south to test the southern grasses for putting green use. So we were fortunate to get one of those 5 northern sites with this green. But what we did is we took the green and doubled its size to make it a 7,000 square foot green. And the next slide. And what we did in-house was we added to that NTEP trial that was growing on a 90-10 Dakota Reed Sedge Ridge Zone mix. And we added these 20 different cells with different organic and inorganic amendments added to the same sand that's recommended by the USGA. The sand that we use is very specific and it relates to particle size and its distribution. And ultimately, it really relates to the pore space. Everything is about pore space, it seems, but this is pore space between the granulars, the sand granulars, not within, like biochar has to offer. So you can see this list of materials. The next slide shows you the balance of the other materials to make the 20 different ridge zone cells. And the ones that really got my interest was the straight sand. How did that behave? And comparing that to the industry standard, which is an 85 by 15 sphagnum peat or a 90-10 Dakota Reed Sedge. Those are percents by volume. And how did those compare with something like yard waste compost with biosolids, earthworm castings? Unfortunately, I didn't know about biochar back then, so biochar was missing from these options. It would have been wonderful if it was included in any of these. But what I learned was, next slide. Oh, so the next slide will show you just the process quickly. So fortunately, we teamed up with Felta Sand and Gravel, who was interested in marketing his sand to golf courses, and he gave a big chunk of his yard at his pit, his quarry, to custom blend all these different mixes, these 20 different mixes for us. So all these are professionally blended off-site. And then as the six-wheeler delivered it, the next slide, each cell then, they're 14 by 15 by a foot deep, were hand backfilled. So you can see it was pretty labor intensive. It was quite an undertaking, but it was fun. And we backfilled all these different ridge zone cells and grew them in. And the next slide will show you, we've learned a lot in many different ways of how these greens mature over time, how they grow in, the disease susceptibility, etc. But right now we're going to focus on organic matter. And let's just look on the left side. This industry standard for us is identifying the percent organic matter, what they say lost on ignition at 360 degrees Celsius. So that is how we kind of determine the percent organic matter. And if you look at the blue bar represents that straight sand cell. So over 19 years time, we did this a couple years ago now, that straight sand did get dirtied up, we'll say, with some organic matter, about 0.25%. So as those roots grew and died back, as the biology grew and died, and we added as spray-ons and organic fertilizers we used, at the end of the day, the straight sand did pick up 0.25% of organic matter. So it's true down deep that 12-inch mix did get some organic matter deposited from the plant. The next bar is our industry standard sphagnum peat. What this bar shows you that it started out in the apparent original mix near 1%. Now remember, that's 85 by 15 by volume, but doing the test on loss on ignition at 360, it's 1% organic matter. And over 19 years' time, it went from 1% to about a half. So we lost half of that peat, actually more, because you can assume that some of this material, this organic material, is being deposited just like in the straight sand. But at the end of the day, that settled down to be 0.5% from 1. The next bar up, the gray one, represents another industry standard, which is reed sedge peat. It tends to be more stable, and it shows that here. It started out about the same, about 90%, almost 1% organic matter. 19 years later, it's at 3/4. So we lost 23% of that organic matter. The best performing one, as it pertains to the stable organic matter, was our composted biosolids and yard waste compost. So that started out just a little bit over 1%. It lost 19%. So at first that surprised me because I thought maybe that material would be more biologically available and utilized. But then I thought about it. Peat is kind of in an anaerobic state. Once it's harvested from these bogs, it's introduced into another environment with oxygen and different kinds of biology. So some of that carbon is going to cycle out probably fairly readily, where compost has already gone through that thermophilic composting stage that's going to bring out material that's a little more stable. So the next slide then shows you that what we've come to learn, which is that top 4 inches of material of basically that matte thatch layer that developed over time, especially through sand top dressing, created a layer that was close to 2% organic matter. So basically, for those of you that's not really into golf, what we do as a practice is we top dress with straight sand to try to smoothen the surface. It helps against some diseases like anthracnose. And it's a way to try to address imperfections in the surface like ball marks and footprints, perhaps, or spike marks. So it's a common practice to go out there pretty often, sometimes once a week, every other week, depending on the growth cycle of the plant. And we put a light layer of sand down. And that sand commingles with the surface organic matter and dilutes it, but basically converts it to soil organic matter as that surface organic matter commingles with the sand and becomes part of the growing medium. So that 12-inch deep root zone that we started with grew an additional 4 inches in 19 years' time. That's how much sand we put on the top. And what we discovered was that upper layer is significantly different than the bottom layer, the original 12-inch layer. And this shows you as an example. This is a straight sand, comparing straight sand, which again ends up being about 0.26% organic matter, which is 7.5 times less than the 2% or 1.95% organic matter that's in that top 4 inches. So that's like the worst case scenario. So some people feel like building these sand-based systems out of straight sand is a good thing. I question that because of this scenario, the way this thing evolves. Next slide. Here's another example of the better one, which is the more stable one that we saw, the composted biosolids yard waste. Again, that matured out to be 0.91% organic matter, which is only 2.1 times different than what the organic matter is on that top layer. So basically, the overall goal, if you look at the next slide, for example, that kind of shows you the visual. You can see that top 4 inches. You can see it's browner, hopefully, in the image. You can see the sand looks cleaner from that point where my finger is. And that's the original mix. From my finger down to the right is the original mix. From my finger to the left, where you can see a little bit of turf, that's the top dressing, what I call the top dressing horizon that we built on top of that green from top dressing. So that area to the left has, at best, 2 times the amount of organic matter than the material to the right. And as you all know, with more organic matter, you have higher water holding capacity, higher CEC. The biology is different in that zone. The pH is different. And ultimately, what we kind of created was like a biofilter on top of the original mix. So everything that's applied on the surface, which is most everything we apply, whether it's fertilizers, biostimulants, even water, it gets trapped in that upper surface and never really gets a chance to get down deeper very easily. So that over time, there's really no reason for the roots to get down in that original mix anymore. So that upper layer becomes your root zone and all the action's up there. And it could get soft on you. If that organic matter is too high, all your roots, like I said, are found up there, and you leave the original mix behind in 20 years, less than 20 years time. And that just, that's really not our goal. And if you pull on it, like you see on the image down below, you'll see where the roots start and stop. The roots are all in that upper surface. The ideal thing is to have those roots explore and continue to exist deeper down, which allows you to use less water, less nutrients, and the surface to get drier, which means it would be firmer. So the goal is the challenge is how can we better match those 2 horizons, the original mix with what you're building on the top with the aid of the plant. And that's where biochar's persistence is attractive, its CEC and water holding capacity ultimately is all attractive because biochar could be added to that mix and in such a way where you're not going to interfere with the pore space between the sand particles like clay or other forms of organic matter may do. They may interfere with that pore space and then that sand root zone goes sideways really fast. That pore space is very important among those sand particles when you have such a high percent sand in a root zone. The next slide. So the vision is to the left is what I would consider a healthy growing medium with a nice consistent flow of organic matter from top to bottom and consistency in overall soil texture and structure compared to, say, the right, where you either have a thatch layer or heavy mat layer. And as the saying goes, layers may be good in cakes, but they're not good in soils generally. You need some thatch, you need some mat for sure with resiliency, but the goal is to try to find that fine line of having just enough but not too much, which starts to interfere with water and air movement. And when you get such great differences, whether it's in texture or in organic matter, and that water starts to change in its infiltration and percolation, then you get things like sulfur, basically it's iron precipitate they call it, or we call it black layer, where you get different zones of different levels of oxygen or CO2 or metabolites are developing, and you can get what they call black layer, which is a thing with sulfur and lack of oxygen, or iron precipitate, which ends up being kind of a cementing process, and it can get nasty. Next slide rather. So it's my opinion that I feel that these sand-based systems are fairly short-lived. And I say that, I mean, maybe it's not a total fair comment, but there's 2 things I got to make sure I'm clear on. One is I'm not suggesting that the way things are done today, that these greens all end up failing. The real question is, do the greens perform at the level they were meant to be and designed for, and are they sustaining themselves in longevity to make the payback worth it? And that's the question or the goal. And when you start seeing references were greens last 15 to 30 years. Generally, the 15 is further south, 30 years is further north. I compare that to the greens that I just replaced 2 years ago that were built in the 20s with horses and scoop shovels and technology that doesn't even come close to what we understand today. And yet I was still living with those greens up until 2 years ago, and they were functioning at a pretty high level. These sand-based systems, perhaps if we study them better long term, maybe we can move that needle a little more so towards longer longevity. Next slide. So a couple of years ago, I was fortunate to attend a Biochar conference, and we were trying to stimulate these questions and observations, sharing them. And we made a poster. This was just a poster that we made. I just wanted to show you. We don't have time to go into all this detail, but we are going to cover some of this. But basically, the goal is to raise these questions of concern, share the observations in hopes that the scientific community gets involved and does their thing at a higher level than what we did. I consider this a case study, but it needs to be studied under professional scientists and hopefully with a long-term vision and view on how we can perhaps improve upon these systems and how biochar might fit into that. Next slide. Next. So if you were to graph what I tried to explain, and hopefully it was clear, to the left is how a sand-based system tends to mature, with a top dressing horizon that's got roughly 2% organic matter that is being driven by the thatch, basically the surface organic matter being buried by the sand top dressing, converting it to soil organic matter, which we often call mat. That will grow in depth over time if you continue to sand top dress. And below that, the organic matter actually gets lost through degradation generally, especially if they're peats. Our goal when we built our new greens was closer to a transitional wood zone seen to the right. So the concept is you start with a cleaner mix down below and you rototill in different amendments, char, chip humates, compost, being all part of that, and dirty it up to better marry that layer that's going to develop from the turf system that's close to 2%. So you have this gradual transition taking place from bottom to top, preventing a layer. The next slide. So when you look at organic matter, you can see this. I like this chart I took. I hope I gave it credit, but I don't think I did. I got to get credit on this one. But I try to give credit, obviously, on all the things I take off the internet. And this one was one from the internet that I really enjoyed seeing. And it tells you a lot in one graphic. You can see the organic matter where it says how it degrades from high to low, or grass clippings and manures and whatnot, leaf litter, degrades fairly rapidly. And when you get into lignous type material, that's when things start getting a little more complicated, and the soil organisms have a harder time breaking that down. And that often is what most scientists think starts to turn into more humus-like material. So some of that lignaceous material does get degraded, but some does not. And that's what they call the stable organic matter, which feeds into the CEC of the soil and the water holding capacity. And you can see biochar just to the right of that does the same thing. So if I'm really interested in preserving pore space between sand particles, which these sand-based root zones rely on for their physical function, then I have to be careful what type of organic material I'm going to add into that original mix and not overdo it and plug up all that pore space, which really makes that sand system perform very poorly. So lignous material may have a role in it, but you have to be very careful, because if you overdo it, it's going to backfire on you. But biochar, I felt, is a perfect marriage because it's not going to basically interfere with that pore space. Next slide. So that finally got me to get pretty comfortable with using compost and biochar together. And that got me on this path to start testing it ourselves with the help of Cale Bigelow at Purdue and Steve Vaughn at the USDA, for example, and others, but they really helped me a lot. And when I look back in the literature, it's kind of funny. The next slide will show you that compost and charcoal is really nothing new. This is one of our oldest publications that we have in our field of study. In 1929, there was a whole chapter associated with compost and what they called charcoal, which, you could argue was kind of, the biochar of the day, and how it was important to mix the two, according to this author, John Morley. The next slide, tells you even more that how the effects of organic matter is one of the most important elements in soil. And obviously there's no exception with turfgrass soils. And you can see there's even ads for charcoal that was within that publication. So I found that kind of comforting, actually, but how ironic we tend to go in full circles. Next slide. So this gets back to that study a little bit with the switchgrass that was used as the material, and how it said that the chemical and physical parameters of sand and biochar root zone should be evaluated over time in a field setting to better evaluate the effects of biochar as it is applied in a sand-based root zone. It said that this research shows that biochar is able to provide nutrients and increase nutrient retention as well as increase water retention. So you can see that the outcome was favorable, but I would have loved to seen that same study using, say, either coconut or wood, and perhaps with a different nutrient regime, or perhaps having that biochar pre-treated, especially if it's a short-term study. And I bet the outcome would have even been stronger. But there's at least some work out there, and hopefully over time there'll be even more specific for turf. Next slide. This was just one little segment of it that showed how the bulk density changed and the rooting depth, and you can see the biochar in percent by volume. Back then they used 0, obviously was kind of the control, 5% biochar by volume with that switchgrass, 10%, 15, 20, and 25, and you can see the rooting depth, as an example, started to decrease. So it also showed me that there's a sweet spot somewhere. There's this zone of application rates of this char. More is not necessarily better. And what we found in our studies was, generally speaking, we all know different chars are different, but generally I wasn't comfortable going over 10% by volume. And it was really usually closer to 5%. It didn't take much. Next slide. So we took it upon ourselves to do some field work, and this is replicated. And this is just, I don't have a lot of time to dive deep into this, but this is starting to get in the meat of it. And you can see the different amendments that we added to the same, what we call USGA recommended sand. And we had the 85-15 sphagnum peat as the industry standard. We used a special material that we amended the biochar with, 10% vermicompost plus 5% biochar. Carbonized PN is another, the soil enhancer. That's from Miramichi. That's basically a 50-50 biochar mixed with composted swine manure, 5% of that by volume. Another rep, 10% by volume. So we were testing the two different rates. And then we tested some biochar with the sphagnum peat, with the vermicompost that was rototilled in. So if you can't afford to, for example, to get a custom blend of the whole mix, perhaps rototilling it in and getting that transitional ridge zone established would be the goal there. Same thing with treatment number 7. That was more of a transitional with the material raked in the top, pre-plant, etc. So you can see what the pictures look like down below of the plots and the different colorations they had. Next slide. This shows you the process. So we simulated a USGA ridge zone profile. So the guys cored it out 16 inches deep. This is at the end of one of our existing bentgrass nurseries that we do other research on. And you core it out, and then you add drain tile. And then the next slide shows the pea gravel, 4 inches of pea gravel that bridges with the sand. So that's a pretty specific type of pea gravel as well. It's all about that pore space. And then the next slide shows you basically, oh, then we also custom blended some of the char. This is Dave, who used to work for us, that he had the fun job of mixing some of this micro char with some of these products and regular char with these different materials, pre and probiotics. We actually had to develop our own equipment to do some of this work in, because it's, you know, it's basically working with a slurry. Next slide. And then each cell was hand mixed with a cement mixer. The guys knew the buckets of sand versus how many buckets of amendments. So the ratios stayed consistent. Each material was then carefully collected. And then the next slide will show you what it looked like out in the field, backfilling, being very careful not to cross-contaminate. And you can see again the different colorations of the different amounts of organic material, or what kind of organic material was there. And then when all these were backfilled, the wood was pulled out. The next slide will show then what it kind of looked like. Next. Oh, this shows you example for those 2 reps that we amended from the top down. We basically tried to rototill in those materials, as I mentioned earlier. So that just shows you how we did that. The next slide. And that shows you the start of it, the growing. We used a seed blanket, that cover that was peeled off there, you can see in the background, to ensure that the humidity and moisture was pretty high near the surface to get the seed to pop, and which might cheat a little bit of the results, meaning that if there was a droughtier mix, that seed probably would be a little more retarded in popping. But we wanted to make sure that if we had any kind of rain event that first week or 2, we didn't have any washouts and cross-contamination. So during that initial week, we did have it tarped with that blanket there. Next slide. So that just shows you a little bit of the progression, a little bit about how the different amendments have impacted the establishment rate. Next slide. And then after establishment and mowing it at greens height, you know, we started to observe the different nutrient impacts, the rooting, in this case, dollar spot. You can see those little straw colored circles there. That's our #1 disease that we deal with in the Chicago area, called dollar spot. Next slide. This shows you, for example, the amount of dollar spot that was in this industry standard 8515 peat. You can see it's pretty heavily hit, because we grew this in, by the way, with some nutrient inputs, but no fungicide, no pesticide. And in fairness to the peat, if we would have fertilized it at a heavier rate, I got to treat them all the same. That's the thing, though. So if I would have treated them all with a heavy rate of fertilizer, nitrogen, dollar spot's one of those pathogens that responds, that it really is more devastating under low nitrogen regimens. So if I would have upped the nitrogen in that peat, probably the disease would have been less expressed, but then that would have probably over-fertilized the rest of them. So hopefully that was clear, but all these were managed the same, and you're going to see managed the same. There's a significant amount of difference in dollar spot. Next slide. And here you can see the 85 by 15 peats getting pretty much wiped out. Eventually, over time, that disease started to infiltrate even the good plots. One of the better ones, for example, was the biosilid biochar. Biosilid has a pretty strong nutrient component associated with it, and probably helped made dollar spot, suppress dollar spot better than others. But eventually, the disease came into all of them, but still at different degrees. Next slide. So we try to do some rating. When we have time, it's hard to find a time to construct these things. Usually it's done in the fall, but data collection is usually done during the summer months, and I got to attend to the golf course with the crew. So sometimes the best we can do is just take pictures and then evaluate with good, bad, or worse. It'd be ideal to have numbers associated with this, but sometimes I got to prioritize the crews and my time, and attend the golf needs during the summer, but we still get some information. You can see the dollar spot severity we rated was really severe under the sphagnum peat. Again, our industry standard. You can see the varying degrees of rating on best, fair, good, and severe as far as disease with dollar spot. Next slide. The other thing we tried to observe, and Vitas actually put this graph together, another employee of mine that used to work for me, and he has a master's in soil science, so he was really good at this. And what we try to express in this chart here under the 11 treatments, shown, where the plot number is, the amount of dollar spot that was expressed in the field by the size of the dollar spot icon, how bold it is. You can see number 9 with the biosolids, biochar. That didn't get any dollar spot at this rating, but yet a lot of top growth at the expense of root growth. Number 1 is our industry standard, and you can see, for example, it's rating pretty good except for dollar spot, a little thin on the top, but again, if I would have increased the nitrogen, I probably could have addressed that. So there's our industry standard under a young turf grass setting. And you can see it's performing pretty well. It's got a fair mat layer, which is represented by that brownish bar below the blue. The amount of root mass was extensive. But again, over time, we need long-term studies on how does that evolve over time. And that mat layer, I'm convinced, under that more impoverished system, both in biology and nutrients, and probably some of the phytohormones that are associated with the biology or lack thereof, grows the plant differently. And that plant is really doing what it was meant to do, which is generate a lot of complex organic matter. And if you have a more mature root zone, I'll just describe it as that, for lack of better words, which is more rich in biology and nutrients. It's more active in cycling organic material. That turf plant grows differently in that environment, and the organic matter that creates issues over time is less. So we try to get our hands around that, and over time continue to track this. Next slide. So those are some of the field studies we've done. We've done some top dressing studies too and whatnot, but I just can't cover it all with the time, unfortunately. But we also did some greenhouse work, and we're fortunate to have a little greenhouse. And the next slide, it just shows you some of the different materials. Basically, what we were interested in this more controlled environment is what is growing in these materials. What is a good habitat? Is sand considered good habitat? As seen on the left, you can see what I mean by the pore space is all driven by the pores between the sand particles, where biochar has a different type of pore space in that it's part of the material. And so how does this really pan out with biology? Next slide. And plant health. So we know the importance of organic matter as it pertains to microbes and trying to stimulate microbial activity. So is oxygen, moisture and temperature also, obviously is very impactful. Soil fertility and pH. pH is a big one. And then the niche, the habitat. Clay tends to be in a natural soil system a pretty important element, as long as it's not too much. That impacts the physical component negatively, but some clay is actually very good. That creates the water film and then ultimately the biofilm for the biology to associate itself with, and often the nucleus towards humus. Biochar, I think, plays a very similar role, but unlike clay, it won't plug up the pore space of the sand. That's the problem with clay in these sand-based systems. Again, it clogs up the pore space. And of course, the plant is a big engine towards driving the microbial growth, especially within the rhizosphere. Next slide. So here are just a quick differences. For example, number 4 is the industry standard with the yellow rather, with the sphagnum peat. You can see how thin, sparse the turf is growing compared to number 8, which is the biochar biosolids. So definitely different top growth, you can see obviously. Next slide. And we did a couple different ways. We did one without trimming the grass. I felt that wasn't a fair representation. So then we started trimming the grass and keeping them trimmed. And then we added another rep where we added these different amendments, or different probiotics rather, with the char, with the raw char. And so I don't know if any of these names are familiar, but they're all microbial in nature, whether they're bacillus organisms, Pseudomonas, or Trichoderma, or mycorrhizae, or a mixture of them. And then I've got what I call the shotgun vermi compost extract, or teas. I call that the shotgun approach. And so we pre-treated, the next slide, the biochar. You can see we used mere acid, a type of acidifying fertilizer from Miracle-Gro, as a nutrient source, and Terraplex, which is lignin sulfate, which is an acidifier and has a component of lignin as a carbon source. And we mix these all up equally as a base type material to pre-treat the char with, and then we added the biology. So you can see the top left were the containers with a little bit of the Miracle-Gro and the Terraplex, and then the char added. We mixed them up, put them in our furnace room where it just was warm and dark over the weekend, and that's how we pre-inoculated the biochar. Next. That's again the list of the materials that we used with the char to see what microbes and the impacts it had on plant health. Next. And there's another just visual. You can see the impacts it had on top growth. These different probiotics mixed with the biochar at 10% by volume with the sand. Next. So again, what we were focusing on was turf quality establishment. We couldn't really pick up any information on disease because it's in a greenhouse, and I don't know enough on how to inoculate. But how did the turf grow? What was the physical differences in turf growth? The mat pinch test, we call it, again, how significant of a mat layer was developed, that differed. The root density, color, and strength, and then whether or not the roots went all the way through the 12 inches and into the pea gravel. We try to document that. The next slide will show you, for example, that's the differences in the mat growth. You can see to the left, there's hardly any mat. You can see those seedlings are growing, and it's like the fine root hairs are just going straight down basically. To the middle is a little different. You can see the chunks of char in there. And you can see the far right, you can see the mat layer where those fine roots, the architecture of the root system itself is different, and creating that network of fine root mass that really stabilizes that surface, anchors the plant and the sand together, and which is needed. And especially when it's young, you're really pushing to try to get that for playability. But again, over time, there's a trade-off that if you're too aggressive in getting that over time, that's going to hurt you because of that higher amount of organic matter near that surface. Next slide. So that's another example. We called it the pinch test. You can actually not only see it, but you can feel it. And you can see the different levels of rooting and with the different amendments, cool terras, biochars, what we used in this study with the different biologicals. Next. Again, this is just another visual of how we rated. To the left was pretty thin, sparse turf. Middle was somewhere in the middle. To the right was far more dense, greener, more aggressive top growth. Next. Here's the different roots, what they look like. To the left was very robust, and then all the way to the right was kind of wiry and dark. We're still not sure what that means, but the different chars and amendments actually made the roots grow differently in that regard. Next. And then whether or not the roots were present in all the way down in the pea gravel, and you can see there's differences. Next. So this is what we tried to come up with. Again, Vitas came up with this graphic. It was wonderful. And basically, the treatments you want to see little to no red, or yellow, and preferably all green. And so we try to identify these different characteristics with the different rate dates tied to the different biology that was mixed with the biochar. Next. And we again graphed these different amendments, different treatments on the turf density, quality, root density, root color, the mat test, etc., and try to come up with a visual that we could kind of easily see and grade, so we knew better how we were going to grow or establish our new greens. Next. I just want to mention that Steve Vaughn with USDA has done a lot of this work as well down in Peoria, Illinois. Next. He's actually got several publications out there, and he found very similar observations, comparing again with the peat. Next. And that was the different treatments he had in this rep. He's done several of these. He seemed to do a different one every year. Next. And you can see again, 85-15 peat, pretty sparse compared to the 85 sand biochar biosolids. So very similar observations. Next, which makes you feel, more comfortable. But he did reps with, he knows how to do the numbers. He knows how to do the statistics. So he's got real science behind his efforts. Mine are based, I'd say, more on like observations. But a lot of similar storylines. Next. And then this gets into the really exciting part. Cool Planet was kind enough to come in and spend a day at our greenhouse as we extracted those different cylinder tests. Next. And we took samples, a couple from the field, but mostly were the greenhouse. And they did some DNA work with those different mixes. And so this is what we're trying to do now, is connect the dots. What did we observe in the field and the greenhouse, both in plant health, the plant architecture, and disease, and perhaps even other stresses like drought, and tie that into perhaps maybe some of the players that's involved in the biology. And these are plant growth promoting rhizobacteria. So these are the good guys, so to speak, that associate themselves with the plant. You can see the differences of with these different bars of the different materials that we inoculated the char with. Next. We don't have time to go into details of this, unfortunately, but here's one that's example of the bacillus group of bacteria. Rhapsody is actually a bacillus based probiotic, and so it's kind of not surprising that ramped up pretty high in the bacillus count. But so did some of these others. Biosolids, for example, tended to harbor a fair amount of bacillus organisms. Same with vermicompost. Next. And then the diversity, that's pretty important. So this is important for resiliency and different outputs. It's just not about an individual organism, but it's about really the community of organisms and how they function together with the plant. And so this, hopefully we can tie this information over time. Next. This is just, you can't see this anyways, but these are all the organisms that their DNA analysis picked up. Next. Fungal pathogens. These are diseases that really we don't concern ourselves too much with turf, but at least out in the field. But that was just another fungal count that they ran. Next. Trichoderma is a good guy, known good guy, pretty well studied fungus. And again, let's see, where is it? So root shield, you see root shield just to the left of center, pretty high bar. That's a Trichoderma herasium, for example. So there's no wonder why the Trichoderma was a little higher in that count in that material than some of these others. Next. Fungal species diversity. I really feel like the turfgrass system, when you look at it as a community with its biology, I think the fungal community, my gut just tells them the weak link. It seems like the turf itself is pretty effective in growing the bacteria, but perhaps it's the fungal community, especially in a sand-based system, that is lacking in its robustness and diversity to maintain a high level of function. Next. And again, just the different organisms that they tested for. Next. And there's some of the conclusions. And one of the best ones was adding the vermicompost with the Coolterra, clean biochar with coconut hull as the parent material was one of the better combinations, but there were several that were good. Next. So real quick, this is how a green's constructed. You core out the green, 16-inch depth. You add the herringbone drainage system. Next. That's our 18th green. Then that's our list of ingredients. Each one of these Vitas measured out, and we pre-calibrated the equipment that spring. And there's a list of materials that we used. There's a pre-plan amendment, several different types of biochar from different suppliers, for example. Coolterra, Miramichi, both were well represented. 2 different parent materials, 2 different, I think, completely different materials in the sense that one was already preconditioned with the compost. Coolterra, I felt like I was able to manipulate more so. Next. So all those solid materials were all added and pre-measured for each green. Next. And again, applied individually. And this is the Coolterra. And what we learned with that, for example, was in the spring of the year when the humidity was low, when we did all the pre-calibration, it changed that the material attracted moisture, and so we had to readjust our calibration on that one and help it along. But different spreaders worked better for different amendments. Next. And then the liquid products too. Some of these products are only available in liquid form, so those were done the same way, measured out. Next. And then made into a slurry. Next. And again, we had to make special equipment to apply it. This is an old sprayer that we kind of rehabbed and put an aeration system in there. So the aeration system helped keep it not only stirred up, bubbling around, but also contributed oxygen. Next. And then this is what I mean by pre-treating the Coolterra. So with everything on the surface still, we put this slurry down with nutrients, pre and probiotics, in hopes that that clean biochar will soak up these materials and be a way to pre-treat it. Next. And then we rototilled it all in, top 6 inches roughly, with the Rotodarian, real nice rototiller. Next. The seed, we use a 3-way blend of Creeping Bent, 007, Mackenzie, and Flagstick, all good plant genetics, but with a diverse background. Next. And even some of the different seed treatments included biochar, including this product here. This product had some fine char mixed in with some probiotics, also with different microbes. Next. And then we added some of our own microbes on top of that as well, like this actinovate. And together, next. All these probiotics mixed in with some little bit of char as a carrier, was hand blended, hand mixed all the seed. So it's basically a seed treatment now. We're trying to inoculate the seed and using char to help that process, and use as a bulking agent to try to apply that fine seed accurately at 1.5 pounds per thousand. Next. And that's what it looked like after 12 days of sowing. Very nice, consistent stand. Next. 2 weeks after sowing, nice, uniform, consistent growing. Nice, healthy plants, good roots already. And then over time, the next slide will show you, we're trying to obviously track this over time. This whole thing is still very young. And so far, I can just say so good, but we're also monitoring the physical components with different labs like Istrict. So we take soil cores once a year, late summer, early fall, and we track the porosity, the infiltration rates, the bulk density, et cetera, and the amount of organic matter in that root zone. Next. And there's just a data set that shows you 1 year to the next. They're 2 years old now, and shows you how the organic matter is changing at different layers and the different infiltration rates, capillary, non-capillary porosity. We're tracking it all to make sure that the system doesn't go sideways and it's maturing the way we want it. Next. So thank you very much. Sorry for the rush near the end there. I probably had just too many slides, but hopefully we can, you can play this back at your own pace and look at slides individually. And I want to thank the different researchers and people that's helped me, some of my peers, but Cale Bigelow and Kevin Jackson at Purdue and Steve Vaughn with the USDA really dove in deep with me and helped me get comfortable with using char on our new greens. Thank you.
Dan, thanks so much. That was extremely thorough. I know there's a bunch of questions, but I just want to say you've given me a whole new perspective on how to look at biochar in terms of it having a personality and renaming feedstock to parent material. I really like that.
It's all about genetics, right?
Yeah. One other thing I wanted to mention before I forget is that one of our members, John Hoffmeyer from South Africa, has put together a brief bibliography of some of the peer-reviewed literature on this topic, and that will be made available to folks on our members-only webpage. So
wonderful, wonderful.
Yeah, so I just want to jump over to some of the questions. Some are broad, some are pretty specific. And the first one is about whether you've tested crushed glass in place of pea gravel or sand.
No, I have not.
Okay. And another question on the slide that was showing the dollar spot intensity. What was the significance of the color of the thatch layer indicator?
So that's a great question. So that pertained to the mat layer and how thick it was and how dense it was. So the darker the brown, the more pronounced that mat layer was. It was thicker, firmer. And again, we need some of that for stabilization and resiliency and for balls as they come into the green to have a proper type of holding capacity as far as the ball itself making impacts. But again, the challenge is if that gets excessive, that feeds into that layered system that can become problematic over time. So you want some of that, but then you kind of want to put the brakes on it and cap out with a healthy layer of it, not too much, if that makes sense.
Yeah. Someone was asking if you believe there is a best biochar feedstock or parent material to optimize soil conditions for...
Seems to boil up to be a favorite. I think coconut hulls are another one, pretty... I call that a strong char. It really has a pretty, it's almost, you can almost use that for filtration. It's so strong, if that makes sense. But until science tells us better, I kind of went with the shotgun approach or the diversity approach, and that's why I use several different chars. And I think trees in themselves offer those variable conditions, because you can just picture like the growth rings of pine trees, right? And the different types of ray cells and cell structure, just the annual growth ring itself. You're going to have bigger cells, smaller cells. So the diversity of that cell, the structure within wood is pretty inherent, where like coconut hulls is probably more consistent compared to wood. Does that make sense? So until science tells us differently on a more targeted outcome that we're after, I'm going to go after the diversity. Some fine, some coarse, some medium cell structure, which wood tends to offer.
Yeah, one of the things that I think we don't test enough for is this notion of hardness or pliability. And also we're finding that the morphology is also important, but it's not something that has been studied very thoroughly so far. Someone was asking about what else is mixed into the cool Terra biochar, which might have been on one of those slides that had teeny tiny writing on it.
Well, we tested that char as a carrier from for the different types of biology that we had access to. You know, bugs in the jug is a nickname, but basically the different materials that are available commercially, some of this are bacillus-based materials, Pseudomonas, these are types of different bacteria, and some of the different fungal, trichoderma being one, but there's different types of trichoderma that we tried to utilize and explore, as well as what I call the shotgun approach, which is our own extracts of vermicompost, for example, that has a whole slew of different microbes that, you know, some we don't even know, and see how cool Terra or any char, or, you know, what role char can play in transplanting some of these known good guys into the field. Because I think it's pretty well understood that when you take these inoculants and try to introduce them into an established root zone, it's very challenging to break into that competitive environment with these known good guys that you're trying to introduce, or ideally a community of good guys, you know. So the concept is, if you can inoculate the char and then deliver the char with the active organisms already associated with itself with that material, perhaps the transplanting process could be done more successfully in the field. Does that make sense?
Yeah. I liked one of the technical names you used on the all of the above, which I think was witch's brew.
You know, exactly. We took them all and mixed them all together to see if we can move the needle. And it's interesting. That was our better performing one, but, you know, I guess this is why you do reps. But there was one rep that just never got off the ground well. We couldn't figure out why. But if you looked, there was one red line through there. So that one rep didn't do well, but the other two were awesome.
Mm-hmm. Yeah, Mother Nature loves diversity.
Yep.
Someone was asking if you could define biosolids in terms of how you use it on a golf course.
How would I define biochar?
Biosolids, sorry.
Oh, biosolids? Well, biosolids, so I know, so they're not accepted with the organic guys, right? They haven't been accepted yet. But for me, biosolids is the biosolids I get from my local MWRD, but I get it for free. So here's a waste stream that's probably studied more than any other organic material that's out there. So I give them credit for understanding what they do. They've gotten a black eye because of the metals, which they've cleaned up largely. So now they're onto the micropollutants as a concern. But I'm not eating this stuff, and they got to do something with it. We make it every day as a society, right? So instead of banging land, waste areas with it, I think turf is a wonderful application for biosolids. It's high in nitrogen, it's high in iron, both things turf loves. And at the rates I use it, I don't feel like I'm loading the system with metals or micropollutants, and I get it for free. So I always felt like that would be a good parent with the char, because char on the flip side, we know char is good for tying up metals, right? So if there is a little bit of metal concern, cambium or whatever in biosolids, char in theory should help lock that up. And my pHs, it's locked up anyway. So, but I think it's a good companion to it when you're using it on non-edible crops, or crops that, you know, it won't pass the organic certification. Biosolids, they won't accept it. But I don't think that necessarily means it's a bad input.
Right, and is it digested, or is it?
Yeah, it's anaerobic. Good question. It's anaerobically digested for well over a year. They're Class A biosolids, so it's the high level biosolids. What is it, Class A 501 or something? But every batch is tested, and like I said, it's probably the most studied input I'll use on that golf course, especially as an organic amendment. And it's like us. I remember I had a little bit of a health issue, and so the doctor wanted to take the MRI, and my wife said, "Danny, don't forget now, the more you look, the more you're going to find." So it's like, you know, So you go in looking for just a simple tumor, but then you find this, that, and the other thing. It's like, well, same with biosolids. I mean, we know a lot about it, and some of the things are raising yellow flags in some people's minds. But, I think if we studied other things to the detail we study biosolids, then maybe we'd find yellow flags there too. But I just feel like the soil system buffers the biosolids. Again, it's free. I get 20 semi-loads a year to top dress my fairways with it, and I use a bulking agent of yard waste compost mixed with it, and it's wonderful. Earthworms love it.
Yeah, great. I'm just noticing the clock here, and I want to check in with both you and Caroline to see if we can extend this for a few more minutes, because we do have several other questions to get to.
I've got time. If you.
With me.
Yeah, okay, great. The next question is about water savings or behavior during heavy rainfall, or a general experience with water management when you're using biochar.
So I have not done any technical data collection on that. It seems to maintain a more consistent moisture level through the sand profile. The reason why the USGA developed this heavily studied root zone, which has got the 4-inch pea gravel, is because it creates a perched water table. So even though it's 90% sand roughly, which will have high infiltration, high percolation rates, the fact that there's a pea gravel layer 12 inches down impedes the water movement until it gets saturated enough where it flushes through. So it's really a water conserving root zone in itself already. So to try to add more water holding capacity is beneficial, but again, to what extent? You don't want it to hold too much water either. So I think biochar tends to have that sweet spot where at 5 or 10% by volume of the chars that I've been experienced has been good. But I'll know better over time. There's this thing called localized dry spots, for example. I'm curious to see how that plays out, or some of the soil fungus creates hydrophobic conditions. I'm wondering, in theory, biochar should be able to help mitigate that a little bit. So I feel like I'm just getting my feet wet with this, with just several years of looking at it. I wish I was 21 years old and starting this all now.
Yeah, we've heard some anecdotes from golf courses using biochar in water constrained areas that it is helping to reduce, but I don't have the data in terms of science on that. I think we'll ask around to see if we can find some more stories on that.
Wonderful.
A question on whether there are any prospects of using biochar on fairways or other sports fields that have turf similar to golf greens.
Yeah, sure. We've got some top dressing studies being done right now, and we're observing that. I think my general gut feeling is, though, the more impoverished the root zone or the soil is, probably the biggest bang you're going to get out of it. I think if you're already in a very mineral, organic, rich soil, like my fairways tend to be, moving the needle might be more challenging from a visual component. My real interest in top dressing with biochar, again, is can we team it with certain biology to deliver disease suppressive organisms at a higher level? It's real quick. It's kind of like if you look at our graduating class or any group of people, you look around the room and you see that person's really strong and is the athlete. That person's really good at math, right? That person's real fast. That person is very social. We all have our different traits and talents, and yet we're all Homo sapiens, and yet we all grew up in the same town, probably eating similar food. So it's no different than biology. You got these microbes that are individuals, we call them strains, that excel at different things. Some of those things could be metabolites that help suppress diseases. Some of them might be ones that create a higher level of biofilm that might help the plant overcome drought. So the idea is not just to deliver organisms, but to deliver organisms, hopefully in a community setting that has these higher level of outcomes associated with them because they're the superstars that we've been able to find out there so far on these specific traits that we're looking for. So if we can use char to deliver those superstars at a higher rate, then perhaps we can move the needle more so than just talking about nutrient and water retention.
Mm-hmm. There's so many other questions. I don't know that we'll get to them all, but just some quick ones here. It's someone was asking is if the biochar is crushed or screened, and maybe a better way to get at that is, do you like a certain particle size for this end?
Yeah, the chars I've used have all been pretty consistent and have gone through a screening process. You know, there's different companies out there looking at pelletizing it now, because one of the challenges with char is used alone is finding the equipment that could apply it nice and evenly. As you know, the bulk densities, you know, it's pretty light material. It doesn't flow very nice, especially if it's humid. So some people are trying to make their char into pellets and then go through a traditional fertilizer easier. Otherwise, you're kind of married to mixing it with material like compost, which I think is a great marriage anyways, or biosolids, and then you apply it through these top dressing type applicators, and that works well.
Yeah, I will say I've also heard that some people prefer biosolids biochar because it is a heavier and a pretty consistent size, but it makes applying it easier. And again, if there's a metals issue, putting it on a golf course is it's not the worst place you could put it. Another question on, do you find applying biochar to be more expensive or labor intensive? And overall, are you happy with using it? Is it something you plan to continue?
Oh yeah, no, I definitely plan to continue. I think as a pre-plant, though, that was my focus. That was probably obvious with the slides as a pre-plant amendment. I'm not interested in putting it on my greens because the reason, again, you know, I'm trying to balance the CEC and water holding capacity. So I'm trying to do things on the top now to prevent a higher degree of that. Does that make sense? The plant's already doing that for me. But certainly in fairway and tee settings, and you know, I could still change my mind too. Again, if they can come up with a way to use biochar to deliver different biology with predictable outcomes, then I would consider putting it on my greens. But as far as the physical attributes, I don't want that surface to get loaded up with something that's going to hold more water and more nutrients, because that's what I'm fighting now with that matte thatch layer.
Mm-hmm. A comment, excellent presentation. How do other superintendents react to your work, and what can the biochar community do to support this?
That's a good question. I think in some people's mind, they think I'm a little crazy, in a sense, a little somewhat radical. You know, like I said, the industry standard is sand top dressing, and I think sand top dressing has done wonders for these old soil-based push-up greens, and that's really why we've been able to live with them for as long as we have. But I'm kind of on this hope that science will dig in deeper, and on these sand-based root zones, I think sand top dressing, I think we need to find alternative ways to deal with that thatch mat layer, and try to balance the pre-plant organic matter with what the organic matter is going to develop near that surface from the turf. And in doing so, you know, my new greens, I'm going to try to sand top dress as little as possible and find ways to harvest and remove the organic matter at the surface rather than bury and preserve. And these are considered pretty radical thoughts right now, but they thought top dressing fairways was pretty radical 20 years ago when I started it, and I still do it. And people tend to sand top dress fairways, and now they're starting to question it over time. You know, a lot of this is long-term stuff. That's the challenge. Some of these things look good short-term, like an 85-15 peat sand mix is great the first 5 years, but then it starts turning. So same thing with sand top dressing fairways. They may seem smoother, but over time they actually become softer. And I'm building my soils chemically and biologically. When you start sand top dressing, you're literally relying on converting the physical the physical root zone on the surface, and you're trying to rebuild this root zone from the top down. You're not amending. You're literally capping. And when you top dress with biosolids, yard waste compost, vermicompost, poultry compost, or biochar, you're amending. And you're improving the soil structure and texture in such a way where the surface gets firmer, it takes water better, it drains better, the biology is better, the rooting's better, the disease suppressiveness tends to come. So it's considered a little different.
I'm just going to get to a couple others, but someone was asking how long you inoculate the biochar with the vermicompost teas or really other blends, and is there a recommended dose to add to biochar?
Yeah, that's a great question. I wish I knew more detail about that, but the greenhouse study, we put those little buckets all mixed up in a darkened room that was warm. It's our furnace room, basically. It's the room that's housed our furnace to the shop. So it's not super hot, but it's a nice warm room, but it's dark. And I did that over the 2-day period over the weekend, thinking that was enough to get the microbes active and have the char associate itself with the different elements. And in the field, we did, I think you saw, we applied that slurry on top of the biochar solids as it was still laying on top of the sand root zone mix, and that was all done in a day. So that, I was kind of relying on a quick absorption there because we had to turn that green over in 1 day's time. We do 1 green a day. 1 green a day it took to apply all these amendments and inputs, rototill them in and get them smooth again. It took pretty much a day for the green, a little less than a day.
One interesting question on does the carbon sequestration aspect of biochar help when you're talking to other golf course superintendents? Is that relevant to them?
No.
Okay. And do you plan on posting any updates of your experiences over time?
Yeah, I'm not a Facebook person or any of that, but I do use LinkedIn, and I do have some YouTube videos out there under Dan D Turf. Dan D, my name, my initial Turf. So occasionally, as I have time and I accumulate things, I'll post on either LinkedIn or YouTube or both. And that's kind of how I communicate to the public, the little bit that I do.
Excellent. We'll try to have that connected in the email that we send out to people, letting them know about the video being available. So that's great. We do have more questions, but I'm going to call a halt to it. And I just want to thank you, Dan, for the thoroughness and all the work you're doing to help biochar get out there in your world. So, Caroline, could you go to the next slide? I do have a few final slides just to let you know about some upcoming events related to biochar. The next couple of webinars that we have, one is a little self-serving. It's about the book that my co-author Albert Bates and I just had published last month. It's called Burn Using Fire to Cool the Earth. If you're an IBI member and you haven't bought the book yet, you get a 35% discount if you're in the US. If you go through the publisher, there's more info on the IBI member webpage. We're going to be doing that sometime in May, haven't scheduled it yet, and then sometime in June we'll be talking about the use of biochar in stormwater, and that's going to be focusing on some work done by Berkeley, Stanford, and Colorado University School of Mines. They're doing a lot of work on that topic. Next slide. So our next biochar study tour is going to be in Finland in early September. And if biochar isn't enough reason for you to join us, I just want to let you know that Finland was voted for the second year in a row as the happiest country on the planet. So it's a great place to visit. And we will be in Helsinki for the first day, talking a bit more about what we spoke about on last month's webinar, which is carbon sink trading. And the following 2 days will be in a place called Tampere. And we're going to be focusing on urban uses of biochar. So we hope to have registration open by the end of March. As long as you're subscribed to the IBI newsletter, you should get notification about that. And if any of you happen to be interested in helping to sponsor this tour, please get in touch with me directly. Next slide. In addition to the study tour, these are a few of the other things happening. Sorry for the hard to read links there. And the one I should really draw attention to is the deadline for abstracts for the US Biochar Conference in Colorado is coming up soon, April 1st. So if you do want to share your thoughts like Dan, the deadline's coming up quick. Next slide. For any members or non-members that joined us today, if you are interested in becoming a member, we have a special offer to encourage you to do that through the end of this month. And we are also going to be sending out a short survey after the webinar. And if you fill that out, it really helps us to improve these webinars and understand what you're most interested in hearing about. So thanks again to Dan and all of you for tuning in today and for your continued support of IBI. Thank you.